Hello everyone. Today we are going to study about the MOSFET field effect, that is metal oxide semiconductor field effect transistors. In the previous video we studied about the GFET, that is the N-channel GFET and the P-channel GFET, and its working principle, constructions, and its transfer characteristics and drain characteristics of the N-channel GFET and P-channel GFET. Now let us study the next concept, that is nothing but our MOSFET, that is metal oxide semiconductor field effect transistors, the other kind of FET. So in the metal oxide semiconductor field effect transistor, we can look into this. We have the substrate. We have the substrate. Along with the substrate, we have the terminals as source, drain, and gate. Source, drain, and gate. A p-type substrate, right? The metal oxide semiconductor field effect transistor is a transistor which is used for amplifying or also for the switching the electronic signals, right? So your let us study, that is we know MOSFET is of two kinds, or it is of two types. One is nothing but the enhancement MOSFET and the depletion type MOSFET. When you look into this, it is going to have four terminals, that is along with the body of the body is also one terminal, but which is always in the grounded form. The body of the MOSFET often is connected to the source terminal, making it as a three-terminal device like other field effect transistors. Because these two terminals are normally connected to each other internally, only three terminals appear in electrical diagrams. The MOSFET is by far the most common transistor in both digital and analog circuits, though the bipolar junction transistor was at one time much more common. So let us look into the logical symbol of the MOSFETs. We have the JFET shown here, and similarly we have two kinds of MOSFETs. One is depletion mode MOSFET and the other one is enhancement mode. So this is the symbol for the depletion mode MOSFET, and the logical symbol for enhancement mode MOSFET is as shown, right? So let us look into the different kinds of MOSFET, that is depletion and the enhancement type. So let us first look into the depletion type MOSFET construction. When we look into the depletion type MOSFET, we have for the N type, that is for the N channel MOSFET, we call this as N channel MOSFET. For this N-channel MOSFET, we have the P-type as a substrate, P-type as the substrate material, upon which the N-type regions are created by diffusion. The N-type regions are created by diffusion. An oxide layer of silicon dioxide, that is oxide layer of silicon, which acts as an insulator, covers the entire p-type and n-type regions. By etching the proper openings through the oxide layer, metal contacts for source and drain are done, right? So source and drain are made. The gate contact is formed on the surface of the metal oxide. The gate contact is made on the metal oxide surface of the metal oxide layer. The gate is electrically insulated from both the n-type regions. So this gate is insulated from both the n-type regions and the p-type substrate. Okay, so this is the construction what we can see here, right? So this is what we have. The drain and the source connect to the n-doped regions. These n-doped regions are connected through an N channel. This N channel is connected to the gate via through a thin insulating layer of silicon dioxide, and N-doped materials lies on a p-doped substrate that may have an additional terminal connection which is called as a substrate. Now, insulator refers to it as a dielectric material. It sets up opposing electric field within the dielectric when opposed to an externally applied field. The fact that silicon dioxide layer is an insulating layer means that there is no direct electrical connection between the gate terminal and the channel of a MOSFET. It is the insulating layer of silicon dioxide in the MOSFET construction that accounts for the very desirable high input impedance of the device. So metal. For the drain, source and gate connection for the proper surface in particular, the gate terminal and the control to be offered by the surface area of the contact. Oxide is a thin insulating layer and semiconductor for the basic structure on which the N and P type regions are diffused. MOSFET is also called as insulated gate FET or IGFETs. Okay, so it is also got a name of IGFET. Now let us look into the basic operation of the metal oxide, that is depletion, depletion kind of MOSFET, depletion type of MOSFET and its characteristic. So when we look into this, we have the p-type substrate and the n channels. Between n channel, we have the n channel running from throughout the p channel, and on that we have the silicon dioxide layer, and proper holes are done to dope the n-type material to form a source and drain, right? So this is what is the construction principle we studied. Now let us look into the working principle. So VGS would be made equal to 0 and VDS is applied across the drain. So VGS is the gate source voltage that is made equal to 0 and VDS is applied across the drain to source terminal. VDS is applied to drain. This results in the attraction of free electrons of the n channel to the drain. Yes, n channel to the drain, and hence current flow. So what actually is happening here means n-channel depletion type MOSFET with VGS equal to 0 volt and applied voltage VDD. So what actually is going to happen here is, because the oxide layer is an insulated layer sandwiched between the conductive regions. So these are the two conductive regions. Yes, a capacitor effect could be formed here. The metal surface which is gate. So let me show you in the next slide. So look here, what is happening here is, I can say, since it is an insulating layer, the capacitor effect is formed. The metal surface which is gate, and the conducting substrate below as is going to act as a capacitor plate. When a positive charge is applied to one of the capacitor, as a corresponding negative charge is induced on the opposite plate. Yes, so the corresponding negative charge is induced on the opposite plate due to the electric field between the plates. The positive potential at the gate induces negative charges in the p substrate. This charge results from minority carriers attracted towards the area of the gate. As the number of electrons reaching the region increases, the n channel is formed gradually and resistance between source and drain decreases. Thus, the resistance by the drain source supply VDS depends on the voltage applied to the gate VGS. So, greater the gate potential, lower the channel resistance, and higher the drain current ID. So this process is referred to as enhancement, and the resulting device is called as enhancement type MOSFET, right? So this is about the enhancement type MOSFET. Now, looking into the characteristic, so let us have a look of a characteristic, what actually it is going to happen with respect to the characteristic. In this case, as the gate voltage, as the gate voltage increases, so we can see here the channel is depleted of charge carriers, thus increasing the effective channel resistance. Such a structure we have is shown. So what is happening here is, we can observe Here, the region below the gate is doped with N-type material. Therefore, there is a continuous N-type channel from source to drain through which current can flow. If a negative voltage is applied from the gate to source, the negative charges on the gate induces an equal amount of positive charges on the other side of the oxide layer. This results in the recombination of holes and electrons in the channel and reduces the number of free electrons available. This makes the channel depleted of free charge carriers, which increases the effective resistance of the channel. As the VGS is made more and more negative, the channel resistance becomes more and more, resulting in less drain current. If a positive gate potential is applied instead of the negative gate potential, the device acts similar to the enhancement type. So as VGS increases positively, yes, so let us speak, as VGS increases positively, free electrons are induced in the N channel, which enhances the channel's ability to conduct, and ID increases. Thus the depletion type MOSFET is now going to act as an enhancement type MOSFET here. So depletion type MOSFET can act as both depletion type as well as enhancement type. So this is what is the characteristic curve. So as and when the VGS becomes positive, I can say my depletion kind of MOSFET is going to act as an enhancement type. So depletion type MOSFET can operate in two modes. That is, let us have, so depletion mode. So two modes means we can see here it is transfer characters. This is what is the two modes. So depletion mode. This is what is the depletion mode. So the characteristic are very similar to the JFET. When VGS equal to 0 volt, it reaches IDSS. When VGS is lesser than 0, ID is lesser than IDSS, and the current is given by the same Schottky equation. Now, when we go for the enhancement type, as already discussed, we know as and when I make the VGS as positive, my depletion mode of D-type MOSFET can be used as an enhancement type. So, my depletion mode D-type MOSFET can be used as used in enhancement mode also. But when we make our VGS as positive polarity. So these are the symbols of N-channel D-type MOSFET and N-channel D-type MOSFETs and P-channel D-type MOSFETs. Similarly, P-channel depletion type MOSFETs. These are the different kinds of symbols we use. So let us come for the N-channel, enhancement type MOSFETs. In the enhancement type MOSFET, let us study about the N-channel MOSFET. So here the same working construction, the drain and the source connect to the N-doped regions. The gate connects to the P-type doped substrate through a thin insulating layer, that is silicon dioxide. There is no channel. The N-doped material lies on the P-doped substrate that may have an additional terminal connection. Now, when we come for the working principle, for VGS equal to 0, the current ID would be equal to 0. For VDS, some positive voltage and VGS equal to 0, making my VGS as equal to 0 and making my VDS as positive voltage because it is a enhancement type. Two reverse biased N junctions, and no significant flow between drain and source. For VGS greater than 0 and VGS greater than the positive voltage and VDS also greater than 0, the positive voltage at great pressure holds to enter deeper regions of the P substrate and electrons in the P substrate, and the electrons in the P substrate will be attracted to the positive gate. The levels of VGS, we can see the capacitance effect acting at the gate terminals, right? So the levels of VGS that results in the significant increase in drain current is called the threshold voltage VT. As and when we make our VGS greater than this threshold voltage, I can say my my ID would be equal to 0 milliampere. So let us look into the characteristic curve of E-type, that is enhancement type MOSFET. The enhancement type MOSFET operates only in the enhancement mode. So VGS is always positive in my enhancement mode. Remember, when we make our VGS as positive, this is going to work in the enhancement mode. As VGS increases, that is more and more positive potential is applied or voltage is applied, ID is going to get increased. As VGS is kept constant and VDS is increased, then ID saturates to a current IDSS, and the saturation region VD-SAT is reached. VD-SAT can be calculated by using the formula VGS minus VT. Now, let us look into the transfer curve and the drain curve. So, to determine the ID, we have the formula as K into VGS minus VT whole square, where VGS is the gate source voltage and VT is the threshold voltage or the voltage at which the MOSFET turns on. K is a constant, can be determined by using values at a specific point, and the formula for K is ID on by VGS on minus VT whole square. So this is what is the transfer characteristic. As and when more and more VGS is made as positive potential, we can see my ID current is going to increase. So this is nothing but the ohmic region, and this is the saturation region. Similarly, when we come for the drain characteristic, we can see a plot of ID versus VGS by keeping the VDS constant. So I can say as of in JFET it was reaching 0 milliampere when we made it more positive. So but here what is going to happen, the current is going to increase. These are the MOSFET symbols. I hope this video is beneficial for you. Thank you for watching.